This video talks about the types of decision errors we can make when we do hypothesis testing. Hypothesis tests are not flawless. When we're using data from only part of the population, the sample, to try to make conclusions about what's true in the whole population, even if we conduct our test properly, it's always possible that we could make a mistake. In the court system, innocent people are sometimes wrongly convicted, and the guilty sometimes walk free. Similarly, we can make a wrong decision in a statistical hypothesis test as well. The difference is that we actually have tools necessary to quantify how likely we are to make each type of error in our statistics. In hypothesis testing, we have two competing hypotheses, the null and the alternative. And we make a decision about which one we believe might be true based on the sample data. But it is always possible that our choice might be incorrect. In truth, either the null hypothesis is true or the alternative hypothesis is true. And we'll either decide to fail to reject the null hypothesis or we will reject it. When the null hypothesis is true and we fail to reject the null hypothesis, that is a correct decision. And when I say a correct decision, what I mean is that the conclusion of our hypothesis test matches what's actually true in the whole population. On the other hand, if the null hypothesis is true, but we reject the null hypothesis, we are making a mistake. And this type of mistake has a special name. It's called a type 1 error. Now, this can occur when we have sort of a weird sample that is inconsistent with the null hypothesis, but it did in fact just occur by random chance. It was sort of a very unusual occurrence, but it did occur by chance. We could end up with a type 1 error. And this wouldn't mean that we didn't conduct the test properly. It would mean that we just simply got a sample that was not representative of the population and didn't allow us to make a correct decision. Now, if the alternative hypothesis is true and we reject the null hypothesis in favor of the alternative, that again would be a correct decision. But if the alternative hypothesis is true and we fail to reject the null hypothesis, then that's what we call a type 2 error. Now, type 1 error, the probability of type 1 error, we use the notation alpha to indicate the probability of type 1 error. And we use the Greek letter beta to indicate the probability of making a type 2 error. Type 1 error is rejecting the null hypothesis when the null hypothesis is true. A type 2 error is failing to reject the null hypothesis when the alternative hypothesis is true. And generally, because we only have data from the sample, we won't know what's true in the population. So we will never know if the null hypothesis or the alternative is true. And because of that, we'll never know if we're making a type 1 or type 2 error. Often we think of a hypothesis test as a trial. If we think of it this way, then it makes sense to frame the verdict in terms of the null and alternative hypotheses. In the American legal system, the defendant is presumed innocent until proven guilty with evidence that is beyond a reasonable doubt. So our null hypothesis, what we'll sort of consider the status quo, is that the defendant is innocent. The alternative hypothesis, which we're seeking evidence to support, is that the defendant is guilty. trying to prove the defendant guilty, is what the prosecutor would be doing. So we can think about the types of error as being analogous to making these decisions. Finding the defendant not guilty when they are actually guilty means we haven't rejected the hypothesis of innocence, but really they are. So this would be failing to reject when the alternative is true. Failing to reject, that's our type 2 error. Finding the defendant guilty when they're actually innocent. Here we would be rejecting the null hypothesis that they're innocent, concluding that they're guilty, but really the null is true. That's our type 1 error, rejecting the null hypothesis when it's actually true. When we're choosing a significance level for a test, it's important to understand that the significance level is related to the chance of making errors. The significance level of the test is actually set to determine the risk of making a type 1 error. So for instance, if you choose a 5% level of significance, that means that you are willing to take a 5% chance that you'll reject the null hypothesis when it's actually true and make a type 1 error. Choosing a significance level of 5% or 0.05 is traditional. However, it is sometimes helpful to adjust the significance level based on the application. We may select a level that is smaller or larger than 0.05, depending on the consequences of any conclusions reached from the test. So suppose we want to protect against type 1 error. Sometimes making a type 1 error is dangerous or especially costly. For example, asthma is well controlled in most people using an inexpensive medication with relatively mild side effects. A pharmaceutical company is testing a new medication that is very expensive and has potentially serious side effects to determine if it's more effective for controlling asthma. Now, the null hypothesis here would be that it's not more effective. The alternative that we're seeking evidence to support is that it is more effective for controlling asthma. Making a type 1 error would be rejecting the null hypothesis and concluding that this drug is more effective when it's really not. This would be potentially serious because while most people are already treated effectively with an inexpensive drug with mild side effects, this would be potentially exposing people to an expensive drug with serious side effects that isn't in fact any more effective. So this is a situation where it's potentially more dangerous and more costly to make a type 1 error. Under this scenario, we'd want to be very cautious about rejecting the null hypothesis. So we should choose a small significance level, maybe a 1%, 0.01, so that we demand very strong evidence favoring the alternative hypothesis before we'd reject the null. Sometimes making a type 2 error is relatively more dangerous or much more costly than a type 1 error. For example, there's currently no treatment that cures Ebola, and the fatality rate among people with Ebola is high. A pharmaceutical company has developed a possible treatment for Ebola and will conduct a small pilot study to determine whether it is effective. Now, a type 1 error here would mean that I believe that this drug is effective and maybe continue to study it in a larger scale study to try to prove that it's effective when really it doesn't work. And that would cost the company some money. But a type 2 error would mean that I would fail to reject the null hypothesis. So I would not find evidence that this drug is effective. The pharmaceutical company would probably stop trying to develop it. And in fact, it is an effective treatment that could help a lot of people with Ebola. So In this case, that would be a situation where making the type 2 error is potentially more dangerous than making the type 1 error. In a situation like this, we should choose a higher significance level, maybe a 10% or 0.1 level of significance. This will make it easier to reject the null hypothesis and support the alternative hypothesis and decrease the chance of making a type 2 error. Sample size is also related to decision errors. A larger sample size, remember, makes the standard error for our statistic smaller. Now, since our test statistic measures how many standard errors our sample statistic is from the null value, a sample statistic that is equally far from the null hypothesis will give a larger test statistic and a smaller p-value when the sample size is larger. What this means is that with a larger sample size, the sample statistic does not need to be as far from the null value to reject. So we just said that a larger sample size means that the sample statistic does not need to be as far from the null value to reject. Sometimes small departures from the null hypothesis can be statistically significant if the sample size is large, even though the difference is too small to be meaningful. This is referred to as the idea of statistical significance versus practical significance. Statistical significance only tells you how strong the evidence is that there is some departure from the null value. Practical significance depends on whether the actual departure from the null value is big enough to have any practical meaning. It's important to remember that statistical significance in and of itself does not mean that a result is important. Power refers to the chance that the null hypothesis will be rejected if the alternative hypothesis is true. So power is kind of the opposite of a type 2 error. It's the chance that you'll actually pick up a departure from the null if one exists. Now, a smaller sample size gives a larger standard error. And that larger standard error makes the test statistic smaller and the p-value larger, and thus weaker evidence against the null hypothesis. So with a small sample size, the sample statistic will have to be far from the null value in order to reject the null hypothesis. What this means is that it's important to make sure that the sample size is large enough. Otherwise, the study may not have enough power to detect a difference that is in fact meaningful and important. And we're going to learn more about power and how to calculate power and choose a large enough sample size to make sure we have the power we need later on in the course. Thanks. Have a good day.